All right, and welcome back for video number 2 for section 5.2. 5.2, video number 2. All right, we're going to talk about power functions. Keep in the back of your head that x squared and x cubed business, but let's talk about power functions. Power functions are always of the form f of x equals a constant times x to a power. Okay, where k and p are any real numbers except for that k cannot equal to 0 because then the whole thing would be 0. Here are some examples of some power functions. So in the first one, h of t equals 3t squared. In this example, my k, the coefficient, is 3, and my power is 2. Second function, g of z, is equal to negative 2 root z. So my coefficient in this one is negative 2, and my power is 1/2. Remember, z square root is the same as z to the 1/2 power. And finally, t of x is 331x to the negative 11th. K is 331. P is negative 11. So those are all power functions. All right. Remember when we talked about even functions a while back when we were practicing function notation? Here is some important fact about even power functions. So I'm talking about power functions whose power is even. So we only have one example up here, but anytime the number is even, it's an even power function. So there's a couple important things to know about even power functions. They are even functions, so they satisfy the definition of even functions, that is that f of x equals f of minus x. They are symmetric about the y-axis, which is also true of all even functions, not just even power functions. And here's the big important thing. Their end behavior matches either the behavior of f of x equal to x squared or f of x equal to minus x squared, depending on the sign of the leading coefficient. If the leading coefficient is positive, it's going to look like x squared. If the leading coefficient is negative, it's going to look like minus x squared. So let's look at some examples of those. Here's my first example. H of t equals 3t squared. It's a power function. The power is even, it's 2. The leading coefficient is 3, and that's a positive number. So this guy's going to look a lot like x squared, right? And in fact, it is x squared, just stretched 3. So you can see that looks a lot like x squared. Let's try a little more interesting one. G of z equals minus 1/3 z to the 44th. Again, the power is even. 44 is an even number. Negative coefficient, negative 1/3. So we know it's going to look like minus x squared. And here's a graph of it. It's a little bit light. Let's zoom in maybe a bit. And while it doesn't look like x squared in the middle, you can see the long-term behavior is the same as minus x squared. So minus x squared would look something like this, right? Let's see if I can draw it. It looks something like this, right? But what the important part is not what's happening in the middle. That looks really bad. I'll draw that again. Not what's happening in here. That's not the important. If we're talking about in the behavior, as x goes to infinity, right? As x goes to infinity, this function goes to minus infinity, just like minus x squared. I should say z this time because we're using z as our input variable. As z goes to infinity, g of z goes to minus infinity. As z goes to minus infinity, g of z also goes to minus infinity. Right? Here we go down to minus infinity, here we go down to minus infinity. So since the power is even and the leading coefficient is negative, its end behavior is going to look like minus x squared. All right, and let's look at our last example. 5/4 x to the 10th, even power, positive coefficient. This guy's going to behave like x squared, right? So as x goes to infinity on this one, t of x goes to infinity. So as x goes to infinity, t of x goes to infinity. And as x goes to minus infinity, t of x goes to infinity, just like x squared. All right, so let's talk about, you probably guessed it, odd power functions. Similar idea. They are odd functions, so they satisfy the definition for odd functions. They are symmetric about the origin, and their end behavior matches either f of x equals x cubed or f of x equals minus x cubed, again, just depending on the sign of the leading coefficient. So this really simplifies power functions down. We just look at the power, is it even or odd? Oh, if it's even, looks like x squared. Odd, it looks like x cubed. Oh, is it positive or negative? Okay, positive x squared, negative x squared, positive x cubed, negative x cubed. Let's look at these examples. H of t equals 3t. You might not have guessed this one, but remember the power on this is just a 1, right? So that means that's 1 is the power, so that's an odd number. So this is going to behave like x cubed, right? And in fact, as x goes to infinity, or t in this case goes to infinity, f of t goes to infinity. As t goes to negative infinity, h of t goes to negative infinity. Right? Let's write that down. As t goes to infinity, what was this? H of t? Yes. H of t goes to infinity. As t goes to minus infinity, h of t also goes to minus infinity, just like x cubed. All right, let's look at this guy. Just going to zoom in a bit. Minus 1/3 z to the 43. 43 is odd. Leading coefficient is negative. This guy's going to look like minus x cubed, right? And so let's see if we can figure out the long-term behavior. And our variable in this one is z. So as z goes to infinity, g of z goes to minus infinity. As z goes to negative infinity, g of z goes to infinity. Right? Just like minus x cubed. And here's our last one. Why don't you pause the video and write the long-term behavior of this one, or the end behavior. Long-term behavior, end behavior are used interchangeably. Write the end behavior for t of x. All right, I hope you guys recognize that 5/4 x to the 17th is going to behave like x cubed. And as x goes to infinity, t of x goes to infinity. As x goes to minus infinity, t of x goes to minus infinity. All right, awesome. So let's just do a quick summary one more time to make sure we have this. If you have an even power and a positive leading coefficient, it's going to look like a smiley face or narrow, wide shape. We don't really care what happens in the middle. We only care what happens at the end when we're talking about end behavior. A lot of weird stuff can go on in the middle, but in the long run, it's going to look like x squared. Even power negative coefficient is going to look like minus x squared. So this guy we think x squared. This guy we think minus x squared. All frowny faces. Maybe they look a little wider, a little sharper, but they all behave the same. All right, and similarly, oops, got out of control here. When we're talking about odd powers and leading coefficients, this guy is x cubed, right? This guy is minus x cubed. That's what we think when we think about their long-term behavior. This one's going to go swooping up from left to right. This is going to go swooping down from left to right. It's really a summary of how to use x squared and x cubed to figure out end behavior of power functions. So let's go over a little bit of formal notation. And I did this as we went, and I feel like this chart is like kind of overwhelming to look at. I probably shouldn't have done it in bright red. It's kind of overwhelming, but we already know this stuff, okay? So the end behavior for a positive even power function is defined by, and this is just x squared, right? As t goes to minus infinity, it goes to infinity. As t goes to infinity, it goes to infinity. Smiley face, right? The end behavior for a negative even power function, this is minus x squared. As t goes to minus infinity, it goes to minus infinity. T goes to positive infinity, it goes to negative infinity. Positive odd power function. That's this guy, x cubed, right? As t went to negative infinity, went to negative infinity, and as t went to positive infinity, went to infinity. And finally, negative odd power function, minus x cubed. Just like that, okay? As t went to negative infinity this way, it went to infinity. T goes to infinity, it goes to negative. So you don't have to memorize this page, just really have clear pictures in your head of x squared, x cubed, minus x cubed. And then these are all easy to figure out. All right, so let's do some examples. Now, we all have graphing calculators with us at all times, but there's some reasons why we want to have these pictures of these behaviors in our head. And that's because lots of times if you put a function to Desmos, you might not have a very good window and you might not be able to see all the things that are going on in it. And if you know the end behavior, then you know you need to either zoom in or zoom out to figure out what's going on. So let's start. What's the end behavior of minus 2x cubed? Well, what's this guy going to look like? It's going to look like minus x cubed, right? It's negative and odd, right? So it's going to look like this, right? So as x goes to negative infinity, f of x will go to infinity. And as x goes to positive infinity, f of x goes to negative infinity. All right, what is the end behavior of 3t to the 8th? First, identify which of our 4 basic toolkit functions this one is, and then identify the end behavior. All right, so it's positive, it's even, it's going to look like x squared. As t goes to infinity, f of t goes to infinity, t goes to negative infinity, f of t goes to negative infinity. Right? Okay, my phone is driving me crazy. What about negative z to the 22nd? Okay, seriously, sorry. I don't know what's going on with my phone. Let's see. It's negative. It's even. Minus x squared, right? Z goes to minus infinity. W of z goes to minus infinity. Z goes to infinity. W of z goes to minus infinity. And finally, 1/8 v to the 11th. It's positive, it's odd, it's going to look like x cubed, right? V goes to minus infinity. W of v goes to minus infinity. V goes to infinity. W of v goes to infinity. All right, that's it for this video. So really the key is to have these little weird pictures like I have drawn up in your head and match up to those behaviors.